This afternoon, so I introduce myself. Okay. So I'm Suhyoung Choi from KAIST, Daejeon. Okay. So if you want to see my copy of this lecture, you can go to my homepage and you can download this lecture there. So last time I was trying to explain what the orbifolds were, definitions were, and I think that many people had to go to a tour, so I think I stopped. But anyway, so let's begin there again. So I stopped at some examples of orbifolds. Right. Right. So I mean, I think that basically you want to think of manifolds as orbifolds and vice versa. But I guess particularly because if you have orbifold, then you can cover it by a manifold in many cases. I mean, in many cases, it's just sufficient to study manifolds instead of orbifolds. But I guess what's good about orbifold point is that I think that there's a lot more example you can produce very quickly. That's I think main attraction of orbifold method, I think. But so for example, so this last example I wrote down. So if you take any surface which is a smooth surface, and then you take some finite points, okay, and then you can just give some order like PQ or S, and then it's immediately you get an orbifold structure because what you do is you remove some open subset, open neighborhood around it, and then you get you attach this kind of orbifold. So you take a disk, and then you quotient by some cyclic group over the P, so which is rotation over the P. And so you get a quotient which looks like this sort of cone, and you attach to this, and then you attach to order Q1 and so on. Okay. So immediately you obtain some examples of orbifolds, which is I guess is not trivial also. So that's the basic, I think, maybe. Let's see. Basic example you can get very quickly. And even if you have some manifold with boundary, then you can just immediately double it to get an orbifold structure. So what you do is for a manifold with boundary, what you do is you take some boundary manifold, and so you take the two copies of it, and since these boundaries are the same, because the manifold itself is the same, you will just identify at the boundary only. Okay? So you get a doubled manifold, in fact. But the main point is that now you can act by G2. So G2 will switch these two components. Okay? And then fixed point everywhere in the boundary will be fixed. Okay? So so what you turn up as a quotient space is this one. So this X will be this double manifold mod G2, and so this was manifold to begin with, this union attached to the boundary, because it's boundary as a half-wall neighborhood. And so once you act by G2, then you immediately get an orbifold, right? Orbifold structure. So this part now will be called mirrored or silvered. So silvered. So the reason you say silver because for each point you have some boundary which is sort of G2 action acting on it, right? So at each point you have some neighborhood which looks like it's a G2 action. So you get another very quick example by getting an orbifold like this. Okay. And and then another more, if you got more example, then you take some surface. So this surface, you could have the smooth boundary, but let's make it piecewise smooth, in fact. Okay, so it's more like a cornered manifold now. And what you do is you sort of mirror these parts, but maybe not at this vertex, but at the vertex you try to give a dihedral order structure, so you get you give a corner reflector structure. Okay, so it's more like a D2 divided by this dihedral group order P or something like this. Okay, so whatever P you want to put in, you can do it. Okay, so and of course interior you always give a trivial group inside. So you just immediately get many examples here. So interior of the boundary curve is given G2 is silver, and the corner reflector you can give any sort of dihedral group structure. So it's very quick actually for surfaces. And right, and so for example now, so if you want to look at some submanifold, suborbifold, so if you take some arc on the surface orbifold like this, and say suppose I want something that goes like this, right? I mean it could even be boundary parallel, but it doesn't really matter. But so then this is going to be one orbifold. So it's one orbifold with the mirrored end. So if you have a one interval with mirrored end, which means you just add the G2 structure at the end. Okay. So you just have so this point will have be a quotient of interval by G2 action, right? So it's just so inside you have trivial group, but in the boundary you just act by G2. So it's very so you get an example of one manifold, and right. So you can make a lot of these piecewise smooth and curves and G2 and dihedral group structures here, and what's interesting is that if you remove so if you have this sort of piecewise smooth boundary with some topology inside, you can choose to silver some parts of it only, like this. And here it will be given some corner reflector structures, but sort of so these parts are not silvered, for example here. Okay, and maybe this part is silvered also. So this with the set singularities. So then this is so the real boundary of this. So now you can consider this as a boundary of the orbifold. So these are not the boundary because they are silvered. Once it's silvered, it's going to be inside. So it's going to be considered interior. Okay, but once not silvered, actually is going to be real topological boundary and the boundary of the orbifold. And this boundary actually will contain this point even though it's silvered. Okay, so the boundary looks like a topological space. It's again an orbifold. So the boundary of two orbifold is an orbifold. Always a boundary orbifold is an orbifold. So that's what happens. And so if you have some arc ending at a corner, so it won't be a suborbifold unless it is the boundary of the surface. Okay, so so something like this will be a boundary suborbifold. But if you have some arc like this, and where these orders are PQ and these are not 2s, then this is not an orbifold, suborbifold actually. So because it's going to not obey some properties. So this is a little bit tricky part of the things, right? So like surfaces, you can always give a differentiable structure to the orbifold structure. So I mean, basically, I started with everything smooth, so it has a smooth structure already. But to define it formally, I just have to show that this U tilde is given a smooth open subset of Rn. So Rn has a smooth structure, and G be smooth. So only thing that I really need is that G is a smooth action, and of course all these embeddings or transition functions, transition maps are smooth. So then M is given a smooth structure. Okay, so. And now you can define smooth form, so one form, two form, all the way up to any dimension just by, so if you want to define some smooth form on this open set, then you have to cover it by some orbifold covering, and so any smooth form here is just the ones that lives here, but is maps under this quotient map. Okay, so just a smooth form here is just a set of smooth forms which are equivariant under the z actions. So that's the way to define smooth forms in the orbifold case. So you don't really actually define it here. It's just maybe some equivariant version of there. And then you can now define integrals. You take some simplices. So if you have some simplices in this orbifolds, right, and then maybe they are complicated. But the main point is that when I say simplice, it means that it can locally be lifted to this kind of covers as a simplex, and then you can now you can even define partitions of unity for these kind of coverings and barycentric subdivisions of the simplex and so on. So you can show that they certainly can define integrals, and you can define Riemannian structure. So Riemannian structure just means that it's an equivariant Riemannian structure on the covers, which patches up well. So that's the only thing that you need. And actually, the exponential maps, you don't really need to define it here. It's just you define it here, but you realize it's G equivariant on each orbit. I mean, each chart, so you can just patch up everything. So and curvature and so on. So it's not a problem. So you can even do Gauss-Bonnet theorem. So which means that if you have this kind of orbifold and you try to find a smooth triangulation, and so the basic point is that if you have a triangle or some simplex, then the interior of each cell, like this face, so interior cell, they have to lie in one strata. So you don't want these cells to pass through some strata in weird way. So in that case, we have nothing we can do, so it's sort of bad. So once you have this kind of triangulation of X, then you define Euler characteristic, orbifold Euler characteristic, but you have to divide by the singularity order if this cell lies in the singularity. So K is over all the cells. So SK means all the K cells, which might lie in some singular sets or something. So you just define by these kind of orders, right? So it's kind of, you have to show actually this exists. So, but it's done quite a long time ago, but it's not formally written up. But sort of not complete actually, but it's clear. So Allendorfer, Weil, and Hoff, you know that this is called Chern theorem, but anyway. So if you integrate the curvature, then you get the Euler characteristic, right? So of course this is a Chern form, not the usual form. But in 2 dimension, you can just use the curvature, right? So you just follow exactly the same thing as in the Chern's proof. So that's what Satake has done in his original paper anyway. So right. So these sort of explains what definition and various kind of structures you can put it in and so on. And smooth topology, you can do everything you can be doing. So now we go to
So your condition of triangulation, the
yeah.
maximal dimension, the simplex of maximal dimension is contained in the smooth part of the case.
Each cell has to lie in some singularity with a fixed order, locally constant isotrope.
So the simplex of maximal dimension
Yes.
doesn't intersect the singularity?
Yes, it's an open cell. Open cell doesn't intersect anything like singularity, right? That's right. So so this open cell should not meet any intersection. Singularities, right? That's right. So now we go to covering spaces. So it's usual topology. Now you go to covering. So if you do some topology, if you do first year undergraduate study, then you have to go to covering space all the time. So, right? So let's take some x prime on orbifold, and you take a smooth map. And so for each point of x, so how do we define this covering map? So the basic idea is that is this, right? So it's better to explain by chalk actually. But I mean, by drawing things, not by words. But anyway, so right. So the basic thing is, so you have one orbifold with x prime as undergrad, and then another one x. So this is p, and so you take some point x, and then basically this will be some quotient of some u tilde, where g is acting on it, right? And this will be chart pi. So not to be confused with the other pi and here. And now you take the inverse image here, and basically the point is that this one has a model, but you can think of it as a u tilde with some subgroup in it, right? Okay. And there's another pi prime. Okay. So the basic idea in topology is that this one goes homeomorphic, but now we change that a little. So I mean, this one is already some quotient. So to be a chart or model of this one, you just take the same thing, but you take the subgroup. Okay, so that's the only thing that happens. I mean, it's only up to isomorphism that I'm saying this, right? So then if you have this kind of property for any x, so for any x you can take this kind of model, and then the inverse image has this kind of model. Of course, this has many other images. Sorry. So each image will have a different inverse image. May have different groups actually. Right. So that's a covering. So now you remember the R2 mapping to pillow. So then that's actually a covering. So we had R2, and then we had this kind of order 2 transformations all over as a lattice it occurs. And so we knew that this one covered this sort of pillow, right, or some tetrapeg or something like this, right? So it looks like a tetrahedron actually, right? But it has 4 points where, so everywhere else it's just trivial, but if you take the neighborhood, then you see that the inverse image is some part of the lattice, right? And some part of it, and then this has so here the model was actually G2 acting as a rotation, but here the group is now trivial, so the inverse image is now trivial. Okay. So another example is if you have if you look at torus, right? So this is simplest example actually. So if you do 180-degree rotation, then this again a pillow. Example is pillow, and that's order 2, right? And then you see that in the ordinary points you will have 2 inverse images, but for this kind of point you only have one inverse image, connected inverse image. But now this has G2 as a singularity, but now the group is actually G prime is 1 here. Should sorry. Right. So that's a sort of example of a covering space. So this is a sort of finite covering, and this will be infinite covering here. Okay. Right. So as in the entrance exam, the graduate course. So you need to sort of define what regular covering map is and that sort of thing. So so this is an example due to Thurston. So let's look at some manifold Y and so let's look at Y tilde, some regular covering with the automorphism group gamma. So this is just the ordinary the master's course thing. So let's define this kind of thing. So let's take U tilde, Y tilde, and then you do this. So this means the right coset of gamma I on the right cosets of the set of right cosets of gamma I in gamma. And then you define this kind of covering. So this is actually just the projection. You don't call it covering because it's disconnected actually. It's this many copies here. And now that you cut it by gamma by the left action, then you actually get a covering. So this is Y, and then this is, maybe this is still disconnected, but you still have some sort of covering here. Where gamma acts like this, so you act by on the left in this manner here. Okay. Right, and then we see that this is actually same. I mean, this stuff, I mean, you look at it, is actually this just quotient by gamma I. So this is, you can realize this covering as this kind of thing, this kind of another object. And now we can do fiber product. So suppose we have a sequence of these groups, and then I want to do fiber product of these things. So remember that fiber product is defined for any topological space. So if you have some bunch of maps from xi to x and fi, so many sequences, then you can always define the fiber covering as something, some object here that goes with the map, but it always will lift. Okay, so it's a universal sort of category theory construction. So now how do I define fiber product? Is that you now just do the product of all these things, okay, and then map it to y tilde, and then you act by gamma in this fashion, and the second factor, okay. So then you realize this is the fiber product in this case, if you have a regular covering, okay. So so this is just topology, ordinary topology, but now. Now the main point is that now we can actually let this gamma be not free action, but it could have some fixed points. Then still this construction will go through, and you define an orbifold fiber product in this way. So this is exactly the same construction, and so that's what Thurston noticed first, I think. So by developable orbifold, I mean something gamma acting on some discrete group, properly discontinuously, but maybe not freely, so it could have fixed point, and then we can find a collection of coverings so that these are not might intersect, and right. So once you have this kind of thing, then you can easily find the orbifold structure by, finding these xi's collections and finding these groups which preserves xi. And if it's empty, then you always say not empty. Then it has to be in gamma I, and it covers y tilde x gamma. So in that way, you can give this orbifold structure. So in that case, it is now a developable orbifold. So in the above example, so if you have a discrete group acting on manifold properly but not discontinuously, then YF is actually the fiber product of the orbifold maps. Okay. And now cone points and corner reflectors again. So if you have some acting on this, and you give a code for all the structure, and the maximal group is this, and then now suppose you want to find some collection of coverings where xi is these kind of things, where dm is divides n, then, or you can find the cyclic group, or you can find by this. Okay, so here I got an example. So right. So let's make us some orbifold by just folding these things, right? So if you fold and fold, then this is actually the dihedral group action quotienting. So this has the orbifold structure now. And what's the covering of this is that when the dm is m divides n, then it will be a covering. So in this case it will be n was 8. So now maybe we can do 4 for d4. And then this will cover D8 by just folding, right? Okay. And you can also do sort of cone type construction, which is that now you can sort of, make these things, right? So this is not working, but anyway, so you can sort of make the, like this. And it will be a cone point now, I guess, right? So you have to sort of, right? It's not working now, but anyway, so right. So the cone points and that sort of thing you can see as an example. And here, if you do a fiber product, it will just be some. If you have something like this, then it will be just union of some dihedral, these corner reflectors and some cone points and so on. So these are just the sort of origami stuffs actually, right? And so 한국말로는, so in Korean it's 종이 접기, right? Paper folding actually, right? So, right. So if you have some mirror points, you can always double. So that's the another thing I want to say is that, so you can always double some manifold with mirror points, so the mirror points disappear. So it's called a doubling here, another type of doubling. So let's cover these manifold by some open neighborhoods like this, UI, ZI, VI, and then you, these are orbifold charts, and then you take -1 and 1 for -1. So you take 2 copies of that, and you make GI act by, so error will be sign, so it will be 1 or -1. So according to sign, so if G is orientation, presuming it is +1, and if it's if it's not, then it's -1. This is one choice. There are other choices actually for S, but suppose I do that. And then you take the quotient by this phi star again. Okay, so for each embedding, you can also define lift, and so you can define the gluing. So basically you get some kind of doubled orbifold. Okay, so this is sort of an abstract definition that probably you didn't need to know. All right. So how do we do this actually? So let's look at it in the picture, so it's much quicker actually. So suppose you have some mirror plane, so some half disk, and so this construction means that so you just have to take these open sets. So these will be for each of them you'll get some kind of open sets, which with a G2 acting on it, right? Okay. And what I do is I have to make 2 copies of these, right? So I just take 2 copies of these. Okay. And now I act by phi, right? So the phi sort of was now acting like this, but now there's a sign. So this was a sort of orientation reversing one. So what it means that instead of acting on this, I have to act with this copy. So now it's the fixed points disappear. Okay. So, but then you also glue it in according to the same way. So what happens was that you are getting this kind of thing. So you get actually 2 copies in topological way, but you these things. So actually, what I get is some kind of disk which covers this kind of this half disk. Okay. So this is a doubling construction, so which kills off all the mirror points. Okay. So it doesn't no longer appears. So for example, if I had some kind of a disk orbifold with all these points are mirrors, and I have these orders P like this, and so what I have is some kind of mirrored things, and then these are corner reflectors, and if I do a doubling construction, what I get is I get some kind of sphere with these singularities 2, 2, 4, 5, 3. So I guess 2 sphere, but has a cone points now instead of these dihedral group order, dihedral groups as so this will be D2, but this will be C2 here. Okay. So this is kind of a doubling construction which everybody can do. Right. So these are this is a pillow example that I talked about before, and so if you double a corner reflector, then you get a cone point, and so if you have a disk with corner reflectors only, then you get covered by sphere with cone points, and so I gave you another example of an orbifold. So this is actually a 333 orbifold, but it's a regular triangle. And what I do is I just have to fold this a little, and it will fold right. Okay, and then it gives you just the orbifold structure is just this folding, right? This paper folding is the orbifold structure in some sense. If you make these infinitesimally small or something, but it is the orbifold structure. And this is actually covered by something like this. So this is actually a torus, right? Torus tessellated by triangles. And you see that if you take the one triangle sort of goes to this triangle, each triangle goes to this triangle, and if you wrap it around, then you get this orbifold as a covering. Okay, so it's this one covers this one. So this you have to know this. Maybe I take an exam right, later on, right? So if you want to play with this again, right. So while you're playing, right? So that's called edge-folded triangle, and then there's a teardrop orbifold with cone point over the end. So suppose now let's define some orbifold that cannot be covered. So how do you do that? So for example, so take some sphere, and you have only one singularity, and then you give an order n cone point over there. So that's just you just cut out the disk, and then you take the quotient orbifold, and you reattach these things. So there's a Cn acting on it, right? So but that one cannot be covered by anything else than itself, because because you can sort of define fundamental group, and you see that the fundamental group is actually trivial. It's going to be trivial. So universal cover is always itself. Or another way to see it is that it has only one thing. This is actually hard to see. So let's not talk about it. So. And maybe a sphere with two cone points with a PQ are relatively prime, that this cannot be covered again. Because again, you can define the fundamental group to be trivial. Right. But on Y, suppose, this has, so in sphere, so suppose you give a P and Q, but you can still define a cyclic action by just moving these, arcs by some angle, and then the quotient is again some sphere with but now the order is just multiplied by m times. So suppose you act by c through the m. Okay. So what I can see is that this one is covered by this, but this cannot be covered. So this is universal cover of this another orbifold here. So let's try to now define what universal cover is. So universal cover is anything that will cover any cover of itself, right? So that's just another kind of a category theory like definition, right? So if you have some orbifold, if you have any kind of covering, then the universal cover is the one that will cover this. Okay, it's another covering, but that's what this definition is. And basically, you were going to prove that it exists by doing some kind of fiber product construction, so that I talked about. So for elementary neighborhood, you can do this, and once you can do it for elementary neighborhood, then you can just sort of patch up and get the universal cover. And you can take the model open set to be just simply connected, and so these are called the elementary ones. And so, for example, if you just have some finite group acting on Dn, then you can define you can see that any covering of it is just Dn by G1 for some subgroup, and the covering morphism is some kind of element of G. You can just see that it's just an element of Z, and so actually the covering morphisms are just a double coset of this form, and the covering automorphism is going to be normalizer here. And if you have some sequence of coverings, and you can do fiber product construction as I explained before, and so right. So any covering is going to be sort of covered by this projection. So for any subgroup, you can do it. So for Dn, it is possible to get this kind of a covering. Right. So basically, so if you have a sequence of orbifold covering, then you can define a fiber product by just sort of taking elementary neighborhoods and doing these universal fiber product construction for each of them, each of the covering, and I mean each neighborhood. And then you see that the natural pasting map will be lifted uniquely, and so you can actually construct these kind of fiber product for any kind of orbifold coverings, right? So this is explanation how to construct these kind of natural patching together, and then right. So basically how to construct universal cover is that you realize that all the coverings are just going to be countably many, and you can do fiber products of all of them, and so with some base point, and then the uniqueness is proved again by this kind of category theory arguments, and it's not very hard. And so finally, so you get the universal cover, and then the group of automorphism is called the fundamental group, and it's going to be denoted by pi1 of y, and these will act transitively like on the fibers. I didn't really, and if you quotient by this group again, then you get y, and the covering, any covering is of the form y tilde mod by gamma. So the covering theory just works here. I mean, without any real modification in this category, I think. So, but again, there's a path approach that I didn't really talk about, but it's actually doable and probably may be better. And the group of automorphism is this, and the covering is called regular if the gamma is normal in pi1 of m. And so good orbifold is the one that has a cover which is a manifold. So once you have a manifold cover, then the universal cover has to cover it. So the universal cover has to be the manifold. So it's going to be developable. But so the very good orbifold is an orbifold with finite cover that's a manifold. So you just have some finite action. And the good orbifold has a simply connected manifold as a universal cover. So we'll be mostly concerned about good orbifolds. So I guess in 3 dimensions, for example, it's kind of now, I mean, the Thurston's conjecture is about how to distinguish bad orbifold from good orbifold, and that's still, I think, is pretty unclear, but so a lot of people are working on it, and let's see. Right. So for two-dimensional, people have classified this, and so if you have some orbifold diffeomorphism, then you can consider what the induced homomorphisms of the fundamental groups are, and so on. So, for example, if you have an annulus with one boundary side is silver, then it has a fundamental group isomorphic to G times G2. And the way to compute it is to compute the universal cover. The universal cover is going to be some kind of infinite strip, so it's easy to see that Dirac transformation has to be that. And other ways, you can use the Van-Kempen theorem. So the Van-Kempen theorem also works here. So for example, if you have 2 orbifolds with some boundary and silver points, then you just remove these open neighborhoods of the cone points and corner reflectors. And then if you have a mirror, and then you keep removing it until you don't have any singularities, and now you start adding these silver boundary arcs, and then that means just extension by G2. And then you add up these cone points by since these cone points have cyclic fundamental group, and this dihedral, corner reflector has a dihedral group, so you can just use basically Van-Kempen theorem to compute the fundamental groups here. So the fundamental groups of 3 over 4 can be computed similarly. Right. So basically in 2 over 4, you can classify them by saying it's just a smooth surface with corners by silvering some arcs and putting cone points and corner reflectors. Those are the all. and then it's just so the classification is just the smooth topology with corners and reflectors and numbers of them and boundary patterns. That's the only thing that you need. So you can prove that, right? Right. So now what I want to do is, do a cut and paste with these two orbifolds because to study the geometric structures. So you recall that suborbifold means that you want to sort of have a nice sort of embedding even in the model, in the charts, in the model case, and the group action sort of preserves these subspaces. Okay, and so in this case we want actually sort of nice kind of embeddings that preserves this subspace structure. So that's why, because we want to do some geometric constructions. So here gamma prime is the restricted group here. So the compact one orbifold is either going to be, so we can start by classifying one orbifold itself. So it's just the closed arc without any singularities, or segment without any singularities. So closed arc means a circle. And a segment with one silver point or segment with two silver points. So these are the classification of one orbifolds. So it's really easy. And so properly and nicely embedded one orbifolds. So there's some definition here. So nicely means that only the boundary will go to boundary, and near the boundary this is sort of transversal. And properly means just topological properly. Yeah. So in non-silver case, so embedded closed arc will, if you want to nice and properly embed it, then it will avoid any boundary here. And if you have a segment with no 2 points, two endpoints, but no singularities in the one orbifold itself, then it will have to end in the boundary because it's nicely embedded. Okay, so nicely embedded means that. So if you have a boundary, then it has to, so one suborbifold has to, the segment can only be nicely embedded if you put it like this, if you have a boundary of this surface, and this is arc here. Right. So in the one silver point case, if you have a one silver point, then the silver endpoint has to end in the mirrored point or the cone point of order 2. That's the only way it can happen. And the other endpoint is ending the boundary. Okay, so let's say this point is singular, then this part has to be silver, or if you have this, then this has to end at cone point of order 2. Okay, so that's the only way it's going to embed in the orbifold sense. And two silver case, you end up in two cone points of order 2 or in the some silver part. So that's the only way you can embed these things. Right. So the orbifold Euler characteristic is just that, for Satake is that you have to divide the group order by for each cell, and so if you have some finitely covered by some another orbifold, then we know that R is the number of sheet, then you just have to multiply by the R. Okay. And so for example, if you have a one orbifold, then the circle has Euler characteristic 0, segment has 1, but segment with one silver point has Euler characteristic 1/2. And if you have a full one orbifold means that if you have two silver points at the end, then it will have Euler characteristics equal to 0, right? And this thing also works. So if you have two orbifolds, sigma 1 and sigma 2, meeting at one orbifold in the interior in the topological sense, and this one orbifold is nicely embedded, like what I said, then you have this additivity formula. So this will also work. This is just like in the topology case, right? So it's, again, you can verify by counting cells and that sort of things, right? And then you can modify these further. So if you have a two orbifold with boundary as a underlying space and m cone points and n corner reflectors or other, and then and one boundary for one orbifold. So by boundary full one orbifold, I mean it's in the boundary, and it has a structure of a full one orbifold. Okay, so it will be like you have mirror points, and then this will be an arc. But this is in the boundary, and these parts are all mirrored, severed, right? So this will be considered the boundary mirror points for these one orbifold, and they are called boundary full one orbifold. And now you can compute the Riemann-Hurwitz formula, and the sigma. Just count the sigma xc. You notice that xc is always in this case some manifold with corners, but in higher dimensions this is false actually. But in 2 dimensions, luckily you always get manifold as x, I mean the underlying space, but in higher dimensions it will fail. And so the Riemann-Hurwitz formula is that you can compute it by just looking at the underlying space and looking at the number, the cone points, and then the corner reflectors, and then you count the number of the boundary full one orbifolds. So this is, I mean, the formula discovered quite a long time ago by, it's actually Riemann-Roch type formula. And again, this is, you can prove it by just cutting and pasting. So basically here, here if you have a cone points, then you have to remove it by some circle. Or if you have a corner reflector, then you have to cut it by some arc like this. So this will be mirrored here, and then this is corner. So you cut it to prove these kind of things here. And using the pasting formula that I talked about. Right. So now we can discover what are the good orbifolds and what are the bad orbifolds. So compact 2 orbifolds will be good except for the sphere with 1 or 2 singularities that I mentioned. So PQ, which is not equal, and the disk with 1 or 2 cone singularities. So the only thing that fails to be good in 2 dimensions is this. So sphere with order PQ and PQ are different, or this kind of disk. So you have a disk which is silvered here, and this will be corner. So this is silvered, and this is silver, and this PQ are different. Okay, so then this is again not good orbifold, so it's a bad orbifold. So those are the classification. And so compact 2 orbifolds are always going to be very good. And so if you have Euler characteristic less than or equal to 0, it's always going to be very good. And so if you have a very good orbifold, so that the underlying space is sort of a pretty compact open surface, and you can compactify it by path compactification, then you can find a very good cover, which is going to be a surface. So once it's a surface, now you can sort of compactify it by S hat, and then now you can sort of find the finite group to obtain S again, right? So in the very good cover, you will always have some finite group acting on it like this. So once you make a completion, then you can extend the F action to get a compact surface at XF. So if you construct things like this, then it's just this is called orbifold completion. So the basic idea is that it's sort of inadequate to just define it by just using some Cauchy compactification is hard. So I just have to cover it by finite group, and then use that topological construction, and then push down to get the orbifold completion here. So the splitting, so I'm going to explain splitting. So if you have a 2 orbifold and embedded circle of 1 full orbifold in the interior of S, then you just cut it, and then you complete this. Okay. So this is I can show you what happens, right? So basically, this is what's going to happen. So for example, this one I just constructed. I can, so this is going to be 1 full orbifold, and I can just cut it here, okay? And then basically I complete this, right? Okay? So then I have to add a circle, actually. So I remove one full orbifold, and I add a circle here. So this is one example of this kind of construction called splitting. And the reverse is called Suhyoung, right? So what you do is you just reverse this kind of process. So I didn't really, right? So you take this and then you try to fold this here, and then you paste with some Scotch tape. And that's called the Suhyoung here. Right. So I mean, once you do this kind of splitting, and then you complete this. So splitting means you have to complete after cutting. So then you get some kind of decomposed components, so it's called a decomposition. And so if it is a disjoint circle and full one orbifold, these kind of things will hold. Right. But there are some kind of another sort of distinguished class of splitting and Suhyoung. So so you suppose you have some kind of a circle in the boundary of a surface, right? And now you can give a silvering by just giving it a G2 structure on the boundary points, right? And that's called silvering. And so this is, you can consider this as a splitting also, because what you do is you remove this one orbifold and then you complete it. Okay, so that's then what you get is now really a boundary. Okay, so it's called clarifying. It makes it into a boundary. So now this was silver, now it's not, and then you can reverse the process, and that's called silvering actually, and it's considered, you can consider it as a splitting and Suhyoung operation. And of course you can do it for boundary full orbifold here also. So for example, you have something like this, and this is silver, then this is silver. So this is one orbifold with two mirrored boundary. Okay. So what I do is I have to now silver these. Okay. So I suppose I silver it. Then you have to give order 2 corner reflector structures there, and that's called a silvering process. And another thing is that clarifying is that once you have 2 corner reflectors that are adjacent, you can just remove this silvering and make it into true boundary. Okay? So that's another topological operation. So I talked about this sort of, so there's actually 4 types of here. So to understand what kind of topological thing we can do to these 2 orbifolds, we have to sort of understand the Euler characteristic 0 orbifolds. The reason we need to do that is that these kind of one orbifold you want to work with has to have some regular neighborhood. So this is going to be annulus of Euler characteristic 0. So we can now classify Euler characteristic 0 2 orbifolds. So these are going to be annulus or Mobius bands, or annulus with one boundary component silver. So it's called the silvered annulus. And disk with 2 corner points of order 2 with no mirror points. So you take some disk, and then you put 2 2s in here. Okay, so that's called a 2-2 disk. Okay, actually, right. This is a 2-2 disk because you have this angle is 180 degree here and 180 degree here. So this will be a 2-2 disk. And another thing is silver strip. So right. Right. So for example, here you look at this kind of strip, and then this you put a mirror structure here and a mirror structure here. So this will be the boundary here. So then this is again Euler characteristic 0. object. And then there's a disk with one cone point and one boundary, full boundary component. So this is it. So you just take some sheet and then you glue this thing together like this, and one side. So there will be one cone point here, and then one boundary full orbifold inside. So actually, I wasn't really doing my job right, and I have to cut it. So I have to make it smooth actually, right? So this should be smooth actually. I mean, right. So this will be order characteristic 0 orbifold. So this is actually no corner here. It's just smooth. Right? Okay. And this with two corner reflectors, order 2 and the boundary. So it's called the half square. So what it is this one. So you take some sheet and then you wrap it here, and then you fold it here and fold it here and fold it here. So these will be corner reflectors of order 2, but these will be mirrored. Okay. So this is another Euler characteristic 0 orbifold. And so it has a boundary. So the boundary is actually this lower side. So this is a boundary full 1 orbifold, right? So that's. Right, so I drew the picture, but I didn't draw annulus and Mobius band or Silbert Lange band. So the first one is a 2-2 orbifold, so you have the two singularities, and 5 is a Silbert annulus. So top and the bottom are actually boundaries. So the dotted ones represent boundary actually, and 6 you have this one, right? So 6 is this, and then 7 is the other one. So it's just paper folding stop, and basically, so if you have a 1 orbifold in the 2 orbifold, then you can find the Euler characteristic 0 neighborhood. It's called the regular neighborhood here. And I draw that, so how these kind of 1 orbifold can occur. So for 1 and 2, it's going to represent the generator. And for 3, it is a mirror set, which is in the boundary. So it's a Silbert annulus, so it has to be in the singularity. And number 4 and 5 I drew here, right? So only way for 1 orbifold has this kind of neighborhoods. It's going to be very close to it, but usually you can find this kind of neighborhoods. So this is called the regular neighborhoods of the 1 orbifold. So these are very important things in topology, actually. Finding regular neighborhood theory. This took us quite a long time. These are very important objects in topology. So the basic theory is that if you have a 1 orbifold, you can always find these kind of regular neighborhoods of 8 types. And so if you remove it, then you can get these kind of. So for 1, for annulus, if you remove L, then you just get 2 annulus. And for Mobius band, if you remove it, then you get 1 annulus. And so on. So for 6 and 7, if you do it, then you get Silbert. Right, sorry. So for example, for this one, if you have a 1 orbifold and then you're removing it, means you just cut it, right? Right. So if you cut it, then you get just 1 open. Right. Oh yeah, 이건 좀 잘못. Sorry, I don't think that's right. But anyway, so right. So anyway, so if you do this kind of construction of cutting, then you again get this kind of another type of 1 among 1 to 8. Okay, so that's what I have. So this process of removing error and completing it is called the splitting. And so now you can also describe Suhyoung, so which means you go to reverse direction. And so you take some annular neighborhood and regular neighborhood, and you re-glue these things. Right. So let's skip these things. And so basically, I can describe what are the Suhyoungs actually. So Suhyoungs actually. So the first type is that you start with some boundary, which is B, and then you take another one and then you glue it. So this is just usual topological construction. Okay, so just gluing things, and so so the first case is when B and B prime are different, you're actually gluing things, and when it's the same, then you have to twist by 1/2 and then re-glue it. So this is just the cross capping. So this is already what you learn in topology. And so these are the ones that doesn't create any more singularities when you do this. And for when you have when you want to create two more singularities, then what you do is you can make it into just silver it, and you make it in everything into circular mirror points, or you can just close it, right? By folding it. So you have a circle here, and then now what I do is I choose some order to transformation to identify this. Okay, so that's called folding actually. So that's another sort of construction that we can do. So identity map is the silvering, and the other is folding. So those are the first two types, and the third type is when you have boundary one full orbifold. So the ones that doesn't construct any more singularities, you take two and then you glue these two together. Okay, so that's one thing. And suppose you have a same. So you just have one boundary component, then what you do is you can just use identity map, then it just means you silver it, or you can do this, which is, so you have some, so